On Monday, we talk about the load curve of a typical day in summer or winter. And we introduced the concept of base load, which is the minimal load the system will always have. So such as you can make some generators, such as a nuclear generator, coal-fired generator, and maybe some of the natural gas generator to power the base load, especially for the nuclear power plant and the coal-fired power plant, they cannot easily turn off and on. So you want them to keep running all the time, just for security and reliability concern. Let's see. Make sure it's recording. Okay. So when we come to the load that is not always running, there'll be an intermediate load. So the probability of such load will be not very low, but it's never reach 100%. So for example, at 9 gigawatt load, so the chance will be 70%. So to power that type of load, you need to have a generator which can easily turn on and off. So you can use natural gas power plant generators and hydroelectric power plant generator. And also there's some load, we call it peak load, which means they appear only at very rare chance. How to make so we're going to use the generators such as the hydroelectric, but we can utilize one type of hydroelectric, the pump storage, and also some of the natural gas to power that type of load. So that will require the generation to be more flexible and to quickly respond to change of the load. Then we introduce the concept of the dark curve, which is because of we have a renewable. And right now, the idea to utilize renewable is try to utilize as much as possible. So if we, like in the daytime, we try to use solar power generator, no matter it's photovoltaic or other type of solar plant, we try to generate electricity. And in the evening or in the early morning, so we can utilize the wind to power the load. Then that will largely change the load curve, and that will cause this dark curve. Dark curve will be very different from a conventional load curve in over 24 hours. So there will be more reliability challenge because you want to balance the load in real time. So in the late afternoon, when around the sunset, and the solar generation will largely decrease, and then you'll need a conventional generator to back up the reduction of a solar generation. So that will cause very large slope. So you need a conventional generator to ramp up the power at a very high speed, such as more than 10 gigawatt in 3 hours. So that is almost at the limit of most of conventional generation. So to solve this problem, you either have those conventional generation running all the time. So they're considered as a reserve or spinning reserve. Spinning reserve means they're spinning, but they're not generating any electricity. But when you need those generators to back up the solar so they can quickly generate electricity, or you want to install a lot of energy storage. Okay, so today we'll continue. At the end of Monday's lecture, we start with its hydroelectric power plants idea. This is the Norris Dam, 24 miles along the 75 freeway. It was built almost like 100 years ago. So the principle of a hydroelectric power plant is very simple. So you just convert the part of the potential energy carried by some water, and then that potential energy will become kinetic energy, will drive the turbine and then it will make the generator to generate electricity. So the calculation of the energy or the power generated by this hydropower plant will be very easy. So the output of power will be equal to the efficiency multiplied by the water carried by the water. Assume the efficiency can be very high because it doesn't involve any heat, it basically just converting the mechanical energy of the water to the electric energy. So if we know the dimension of this dam, we can roughly estimate the size of this generator or the power plant. So you just use the efficiency to multiply the kinetic energy divided by time. So kinetic energy is equal to potential energy. So using those dimensions we introduced, we can get that formula to calculate the power generated by the hydroelectric power plant. We mentioned there's two types of hydroelectric plant, and the first type is run of the river hydro plants. The second, the pump storage hydro plant. The pump storage hydro plant will be the very useful ones to power the peak load. But more common hydro plant will be the first type, a run of the river hydro plant. So such plant is just use a natural river flow. The power output can fluctuate seasonally. So basically you have the river, you build this power plant, and when the water flows through the turbine, it will drive the turbine to rotate and to generate electricity. So the output really depends on the water flow. So in the rain seasons, so the water flow is higher, so you can have a higher generation. But if it's in the dry season, you don't have much generation. But the cost can be very low to install and maintain such power plants. And also they have a very small environmental impacts. The second type that will be more flex, it will more complex. So we need two reservoirs at two elevation. So the bottom part is similar to the first type, but I also built a reservoir on the top of the mountain to lift the water to very high elevation, because the energy generated utilized by the power plant will be equal to the potential energy carried by water. So if I can make this reservoir high enough, so you can roughly estimate the total energy, potential energy relative to this generator, right? You know the height, you know the volume of water, and you can utilize most of the energy to generate electricity, so you can roughly estimate the capacity of this power plant. Because to make this generator generate electricity from 0 to peak value, which is equal to the depend on the largest the flow of water, that can only take a few minutes, because they only just need to change the operation mode for this generator between generating and pumping, because the generator is synchronous generators. It can operate as the generator if the rotor is leading the electromagnetic field. So which means you have the mechanical torque drive the rotor to rotate ahead of the electromagnetic field. So it will generate electricity. And you can also let the rotor behind the electromagnetic field, so that will utilize the electricity. So we'll talk about that later when we go to the section of generator modeling. So the switch between the generator and the motor mode can be very simple. So it only takes a few minutes. So when you need this generator to operate in the generator mode, you just let the water flow through this channel and to drive the generator, and it will generate electricity. For example, in the daytime during the peak hours, but in the evening or in the late evening or early morning, if you don't need that much electricity and your network has excessive electricity, so you can utilize that electricity to operate in the pump mode and to pump the water up to this reservoir to save the electricity as energy. So it can behave as energy storage. So the first time I taught this lecture, I checked the percentage of when we call it the bulk storage, which means the large size of energy storage in the power grid. The pump storage hydro plant take about 99%. But because in the recent years, there are a lot of batteries installed in the transmission voltage level. So that percentage, based on my recent check, has decreased to 95%, but it's still majority of the energy storage in the system. Okay, so if you use the red and the green color to differentiate the energy generated or consumed by this power plant, during the peak hours, it will generate electricity. The water will flow down from the upper reservoir to the lower reservoir. And during the off-peak hours, so it will utilize electricity from the grid. Okay, so if you can keep the balance and you trade the power plant together with neighboring system as the microgrid, or a smaller size of a system, so the total energy can be balanced. So the red color, the peak hours like discharging this energy storage, and the green color means like charging this energy storage. Let's use NORSTEM as a simple example to do some quick calculation. This is not going to be tested by any homework or exam. It just give you some idea. And we can really get a lot of information by looking only at this picture. So if from this picture, I can roughly estimate the length of the entire dam is about like 500 to 600 meter. Let's just put the 570 meter. That's the dimension I can find online. The height is about 80 meter if you can fully utilize the entire height. Efficiency, let's put like 85%. The average power generation, I searched for the data about this the Clinch River flowing through this dam. So the average discharge is about 60 cubic meter per second. In the rain season, that number can reach to maybe about 200, like 3 times of this average value. We can use this one as the Q. Then we can plug in everything to the formula. So we have a power output equal to the efficiency eta multiplied by Q, and then the density of water, the gravity, G, and the height. So we get 14 megawatt. The 40 megawatt is about a third of the maximal generation of this power plant. And if you search for maybe on the Google to find what is the largest discharge for this river in that area, that could be 3 times. So that makes sense, right? So the capacity means when the Q reaches the maximal value, about 200 cubic meter per second. So that will make the power plant to generate the largest capacity power. So annual electricity generation can be calculated by this power, the average power, the 40,000 kilowatt. We just change from a megawatt unit to kilowatt unit. And by 24 hours, 365 days, and we'll have 3.5 times 10 to the power 8 kilowatt hour per year. That's the total energy it can generate. It's just an estimate for the whole year. How many homes can this power plant power each year? So I can find the data from a Google, which is 14,000 kilowatt hour per year for average Tennessee household. So which means it can power 25,000 households. Okay, so that is about 29 to 30%. Because the homes in Knoxville is about 85,000 homes. Okay, so quite a lot. A considerable portion of the residential load can be powered by this single power plant. So you can imagine, because this one was built 90 years ago. At that time, it can power pretty large area of Knoxville. So if I don't have this hydro power plant, but I build a fossil fuel power plant, I can build about the same size. It's 40 megawatt power plant, but it will generate CO2. So let's see how much CO2 is avoided by using this hydroelectric power plant instead of a fossil fuel power plant. If I replace this one by a coal-fired power plant, so for coal-fired power plant, each kilowatt-hour energy come with 1 kg, 1 kilogram CO2. So if you multiply the energy by 1.0, you get 350,000 tons of CO2. Okay, 1 ton of CO2 is about 500 cubic meter. So that's a lot. If you build natural gas power plant, that's cleaner than coal-fired power plant. So each kilowatt-hour come with maybe just slightly over a third of the coal-fired power plant. So that will result in 130,000 tons of CO2. So in the US, there's no CO2 tax or CO2 market. But in Europe, they have a carbon price, which is about $40 to $80 per ton. So if you multiply this number by 40, this one will become about $40 million price. This is like a $5 million price every year. If you're not in the US, we're in the other country, like in Europe, the power plant operator owner, they need to pay that price for carbon emission. Okay, so now let's just talk about the fossil fuel power plants. Fossil fuel power plants operate in the principle very different from the hydroelectric power plant, because the key here, the principle is generating the electricity from heat. Then when we consider efficiency, we have to consider the two types of efficiency. The first one is non-thermal efficiency. The other is thermal efficiency. Okay, we need to maintain both efficiency high to reach a high overall efficiency. But non-thermal efficiency depends on design of the power plant, but thermal efficiency depends on some physical laws. And maybe there's certain limit we can hardly go beyond that limit. So that limit is called a Carnot efficiency. So thermal efficiency, theoretically speaking, cannot go beyond this Carnot efficiency. A Carnot efficiency is the efficiency of a heat engine, which is very ideal heat engine. Yeah, let's talk about the Carnot heat engine. So everybody heard of a Carnot engine, right? Yeah, let's just quickly go over the idea, and we can use the idea to investigate the efficiency of the realistic the fossil fuel power plant. So let's assume we have a two tank. We call the blue one as cold reservoir, and the red one is the hot reservoir. So each tank has infinite size. It can maintain the same temperature all the time, and there's a space or tank. They can change the volume based on the there's a piezo. The piezo can move down and up. And I can decide which reservoir will be fully contacting the tank in the middle. I can make it be isolated from both or contacting either one. So that's what I control. Definitely to implement the Carnot engine is not really easy in reality, but let's just assume. So there will be a full step. The first step is I make the middle tank fully contacting the hot reservoir. So it will make the air or vapor, whatever, inside of the tank to fully to have the same temperature as the hot reservoir. So because the heat is coming from the hot reservoir to the tank, so that will increase the entropy of the tank. And make the air in the tank be have more disorders or uncertainty, so it will expand. So the terminology here is called isothermal expansion. Isothermal expansion means the temperature will remain the same, but energy just is transmitted to the tank. That's the first step. And the second step, I just isolate the tank from the hot reservoir. But because it has already moved up at a certain speed, it cannot stop immediately. It will continue. But when it continue, the entropy of the tank will remain the same. But temperature can change. In the next step, I just make it fully contact with the cold reservoir. So the heat will leaving the tank going to the cold reservoir. So the temperature will be the same with the cold reservoir temperature. And similarly, in the last step, isolated from both tanks. So the compression will continue. So why do I make this full step in such way? Because if I visualize in this plan about the entropy and the temperature, each step is orthogonal to one of the two axes. So for instance, the first step is from A to B. The temperature will remain the same at high temperature, but entropy will go up. Okay, and the next step, I isolated from both reservoir, and entropy will remain the same because the isolated area, isolated tank. So the temperature will decrease. Then similarly, the third step, it will decrease entropy, but remain the temperature same. And last step, it will increase temperature. So the full step make a cycle in this plan is exactly a rectangle area. So that make a calculating the efficiency and the work will be much easier than the realistic engines. So we call this cycle as a Carnot cycle. So in the first step, the heat will come from the hot reservoir going to this tank. And in the third step, the heat will leaving the tank to the cold reservoir. So the volume, the size of the two heats are different. So the gap will be how much work this engine can do. So when the engine is doing the work, that is when the pressure up in the air decrease and the volume increase. That's how it do the work. But in this plan, we didn't show in which direction the volume is changing. But you can get the idea based on the name, right? Expansion means the volume increase. Compression means the volume decrease. So in those two steps, it's actually doing the work. And in the other two steps, is actually receiving the work. So we can, but the net work this engine can do will be the difference between the two heats. So the first heat, based on this plan, we can calculate as this one just equal to the high temperature multiplied by change of entropy. The second will be the low temperature multiplied by the change of the entropy. Okay, so difference will be the work. If we tell in which direction the volume is changing, so you tell this is expansion, this is expansion. So this is the direction of changing the volume, increase the volume, and this is direction of changing the pressure. And in the direction of expansion is doing the work. And that work has to be equal to the change of the heat because of conservation of energy law, right? So this work has to be equal to the change of the heat. And we plug in the top two formula into the bottom one, and we can get the idea. The efficiency is just equal to 1 minus the ratio of the low temperature to the high temperature. Okay, so if you know the low temperature, high temperature, you know the efficiency, the limit of efficiency. And any realistic heat engine will have efficiency lower than this limit. So this is the highest limit efficiency you can reach. So next, we're ready to talk about each fossil power plant. we start with the coal-fired steam turbine power plant. So this is what a steam turbine coal-fired power plant looks like. So this is actually the Kingston power plant. So if you drive to Nashville on the I-40, you'll be when you drive through a long bridge, you will be able to see this power plant on the right-hand side. Okay, so when you drive back from Nashville, whenever you see those chimneys, you know you're actually closer to Knoxville. This could be what the internal power plant look like, but it's not that one. But I just find this picture, so it's just a similar. The coal-fired power plant inside will be similar to this picture. So this figure from the textbook gave the idea of how the coal-fired steam turbine power plant work. It goes through a number of steps. So this entire cycle, if you give it a name, is a Rankine cycle. It's not Carnot cycle. Later, I will show why it's different from Carnot cycle. But we still can utilize the idea of Carnot cycle to estimate the efficiency. So how this power plant operate? So you have the coal is fed from here through some coal hopper and into this pulverizers, and then feed into. So here is the burner. Burner will burn the coal and to generate the boiled water, and it will go through this superheater and become high pressure, high temperature steam. Drive that HP is just high pressure turbine. You drive that high pressure turbine, so the turbine will revolve, and then so the high pressure steam will leave this turbine, and through this reheater, the temperature will increase again. It will come back. Then it's lower than the high pressure, but now it can drive another turbine. We call it the medium pressure turbine. Finally, we can utilize the remaining energy carried by the steam. So it's low pressure turbine. So you already have three turbines connected all on the shaft of the generator. So finally, the generator will revolve and generate electricity. And the steam will leave the turbine, go to the cooling tower, and from cooling tower, it will be fed back and to the reheater, and then finish the cycle. So basically, the generator just utilize the heat carried by the steam, then to convert the energy into electricity. There are some concerns of operating the coal-fired steam turbine power plant. First is take a few hours to start. So that's why such power plant can be utilized as the base load generator, but not intermediate or a peak load generator. So not appropriate for a peak load. So it has large environmental concerns. So they are the major CO2 emitters in the power grid. And efficiency is not high, it's like only 45%. So to calculate efficiency, we can utilize the Carnot cycle formula to give an estimate. Let's assume the temperature inside of the boiler or the burner is as high as 550 degrees C. And the steam leaving the turbine will have temperature through this cooling tower will decrease to about around ambient temperature. Let's just put the 20 degrees C. Okay. And let's just assume other efficiency not related to thermal part will be 70%. Then we can just utilize that formula. But please note when you use this formula, so this is low temperature divided by high temperature. So both temperatures are in absolute temperatures. It have to have the unit of a Kelvin. So if you use degree C, you have that number has to be added by 273, right? So the 20 will become 293. 550 will be 823. So then multiply the non-thermal efficiency, give you the 45% of efficiency. Any question? Next, we talk about the gas turbine power plant. The gas turbine power plant can have much smaller size. You see this person standing next to the power plant, because the idea is basically just like a jet engine. For the jet engine, you have your air going through this compressor, become compressed air going through this tank, and mixed with natural gas, which is the fuel, and there will be a combustion happening here to generate very high pressure, high temperature gas, then drive the gas turbine. So only just have one turbine, not many turbines. So design can be very simple. So the cycle of this type of engines are called Brayton cycle. It's different from a Rankine cycle for a steam turbine generator. So it can start quickly in minutes. So it's good for supporting the intermediate and peak loads. So most of the gas turbine generator is actually used in a combined cycle or cogeneration power plant, not individual gas turbine power plant, because that can give you a much higher efficiency. But if you only just use this gas turbine on its own, the efficiency is similar to the coal-fired power plant. So only maybe slightly higher, which is 46%. So you may wonder, the operating temperature of a gas turbine is much higher, can be much higher than the steam turbine generator. But why is the efficiency still the same? The reason is, so when you increase the temperature of the compressed air inside of this gas turbine generator, and the temperature with the air leaving the engine is also very high. Because the efficiency really, to increase efficiency, you need to make the inside temperature to be very high and outside temperature to be very low. Then you can have a high efficiency. Let's just do a quick calculation. So if I can increase the temperature of the combustor inside to 1400 degrees C, and the air leaving the engine can be very high, 550 degrees C. And if the overall efficiency, non-thermal efficiency is higher, like 90%, because the design can be very small, very can be very well compared to the large size of steam turbine. And so by using this formula, so both low temperature, high temperature largely increase. So that will give you about same efficiency. Okay, so for this specific example, intentionally to make the cold temperature, even I still call it cold temperature, but it's very high, right? This temperature, I intentionally make it be same as the high temperature of the steam turbine. So that can be a very naturally the idea of a combined cycle power plant. Combined cycle power plant is, I have the gas turbine running, and so if it's combined, if a gas turbine on its own, this exhaust can be a loss, but I can make this high temperature air go to another like steam turbine generator to increase temperature for the burner. I just replaced the fuel, which is the coal for the coal-fired power plant. So I utilize this waste, still has very high temperature. So for example, it can be 550 degree, right? So I use this one to heat up the burner. So for this one, I don't need any coal. So this can be the case for if I have a coal-fired power plant, but which is retired. I still utilize the entire facility, but I install a gas turbine generator next to it. Okay, instead of using the coal to heat the burner, I actually use the waste from the gas turbine. Then it's called combined cycle. So gas turbine is running in the Brayton cycle, and the steam turbine is running in the Rankine cycle. Okay, so if I want to draw what those two cycles look like, so neither one is a rectangle, right? But it just finish the cycle, and the area inside the cycle just indicate how much work you can do. And you can see that the two cycles not overlap. The Brayton cycle is on top of the Rankine cycle. Still, the x-axis is the entropy and the y is the temperature. So you see there may be certain step, like well, this step, that has constant temperature. So that indicate for the steam turbine from E to F. So that is actually this step, right? So after the cooling tower, the steam have the same temperature, go back to the reheater, and reheater change from F to A, so that will increase the temperature a little bit. Yeah, so you can just map each step on the right figure to the left, so you can know what that step is. And remembering when the pressure decrease and volume increase, that's the direction of doing the work. So you can imagine, so the work will be done with those two steps. So the heat will be coming from the step from 2 to 3. 2 to 3 is actually the combustor. So when the air and the fuel is, which is gas, is mixed and through this combustion. So that is a key combustion step. So a lot of heat is coming down in that step. And after the first cycle, the Brayton cycle, the heat will be leaving that cycle, but it will enter the second cycle. And finally, a little heat will be leaving at due to this cooling tower. So the change of the heat total will indicate how much work you can do. So those will be the direction when the work is done. Definitely, if you want to drive the both cycle to running continuously, you need to also give it a little work. Okay, so the overall efficiency can reach 60%, higher than 50%, because the overall efficiency will count the areas of both cycles, not just a single cycle. So let's just assume the gas turbine can operate at 46% of efficiency, and steam turbine can operate at 45% of efficiency. The connection between the two cycles will lose 15% of energy, okay? So let's just use those three numbers to do some rough calculation on the overall efficiency of this combined cycle power plant. So assume we have 1,000 megawatt carried by the gas going to the first cycle, the gas turbine, and multiply by 46%, it will generate 460 megawatt power. Okay, so if it's just the gas turbine on its own, the remaining, the other 540 megawatt will be the loss. But now we can utilize that one. Through the connection, you're going to lose 15%. The remaining 540 megawatt multiplied by 85%, it will give you 459 megawatt. So this power will be the heat going to the second cycle. Okay. And this value multiplied 45%. So the second cycle will generate slightly over 200 megawatt. So in total, we have power generated 460 plus 207 megawatt divided by 1,000, we have 67%. So using the combined cycle, we can easily increase the efficiency to about 50%. Any question? Okay, so next one, the nuclear power plant. Nuclear power plant is also similar to coal-fired power plant. It's also based on the steam engine idea, but the fuel is not coal. It's just the nuclear fuel. There are two types of nuclear power plant based on the nuclear reactor. So it can be a boiling water reactor or pressurized water reactor. So efficiency usually lower than coal-fired power plant because for nuclear power plant, the reliability is more important. To tell between the two types of nuclear reactor, so usually for the second type, the pressurized water reactor usually will have the pressurizer. You can tell if you has chance to visit nuclear power plant. But today there are new type of nuclear generators actually being studied or deployed. One type is called a macro reactor, so which can fit into a trailer, so you can easily move from one area to another area to fit into a small building. So it has a less secure reliability concern. If you have more interest, you can go to the Idaho National Laboratory website. They'll have more information on that. I'm considering to make this macro reactor as one topic of your course project. So if you have interest. Okay, so let's talk about the wind. So this lecture I just quickly go through all different type of energy resources to give you an idea on how their principles are. So the wind power is actually carried by the wind, right? So if I know the kinetic energy carried by the air, the blowing air, and divided by time, that will be the power carried by the wind. So that will be the kinetic energy. So if you consider this is the wind turbine. If I consider a cylindrical air, right, going through this turbine, I have the area which is equal to the pi multiplied by diameter of the blades divided by 4, and then multiplied by the length of this volume air, which is equal to the speed multiplied by time. So that we'll be able to calculate total energy. Okay, so this will be the mass of the air, which is the volume multiplied by the density. So do some simplification. So we'll have this formula calculating the total power with the wind. So that's not the power of the generator, it's just the power of the wind. So if we know the wind speed, we know the density, we know the dimension of the wind turbine, and we know when the wind blows through this wind turbine, how much power is carried by the wind. But we cannot fully utilize all the power to generate electricity because we have to consider some efficiency. So there's two factors on efficiency. The first one depends on design. So this one can be close to 100% if you design very well. But second one is a theoretical efficiency limit. That one can hardly go beyond 50%. So why? Let's use this example from Wikipedia. Use this comic to talk about why the efficiency may not be 100%. So if you have 100% wind turbine, okay, and so there's two air balls or maybe two molecules, whatever, flowing through this wind turbine. First of all, if the both balls never touch any blade, right? So it doesn't interact with the wind turbine, which means you cannot utilize any energy carried by those two balls. So there have to be one ball going through and the other ball just touch the wind turbine, drive the turbine to rotate. Okay. So if both balls touch the wind turbine, they never go through, which means the turbine is not turning. So finally, you have to let one go and stop one. Okay, the one you let go, that part of energy will not be utilized. But the one is touching the wind turbine will drive the turbine to rotate. That part energy can utilize. So finally, you roughly you can only utilize one of the two. If you let both go, it will say I've got no energy left. Okay, so I cannot utilize anything. And you can also not like just stop all the air to make a vacuum on the other side. So that theoretical limit usually is about 0.4, 40%. There's a theoretical calculation based on the Betz law. So the value is about 0.593 or around 60%. That is the theoretical limit, no matter how you design the wind turbine. But in reality, usually that coefficient is 40%, 0.4. There are two types of the wind farm. So you can it can be on the land or it can be on the ocean. We call the first type is onshore wind farms. The second is offshore wind farms. Onshore wind farms are closer to existing power grid, so you can easily build the transmission line to connect the wind turbine to the users or to the transmission grid. But the bad thing is actually there are a lot of like visual pollutions. Many people, they don't like those wind turbines, and they can be very noisy. And some people believe they are killing the bird. So actually there are many concerns. But this one will have much less environmental concern. But the tricky part is you have to build the cables under the ocean to connect the transmission grid to those wind turbines. And the maintenance cost can be much higher. So sometimes they need to utilize helicopter to land on each wind turbine to do the maintenance. It's not like the onshore wind turbine. So this pole is actually inside is a building. You have stairs, you can just walk up and to the top, do the maintenance. That's much easier. Okay, so I just finished this slide. So those are all the 4 types of the generator for the wind turbines. Since everybody already took a 325, you know the basic principle of the induction motor. So wind turbine generator basically just induction generator. Induction generator, why do we have 4 types? The type 1 is a very basic induction generator. Okay, so the rotor is just driven by the wind. So by using the gear, I try to make the speed to be similar to the frequency of the grid. But it will still have some impact to the grid. And the second type, I just add a resistor to the rotor. So if you remember how the resistor can change the induction motor, induction generator, the resistor will make the operating region be much wider, stable operating region. The third type will utilize the electricity also generated inside the rotor to go to the grid. So actually you can utilize both electricity on the stator and the rotor. But the rotor will through some AC, DC, DC, AC converter. And the last one has a minimal impact to the grid because it's completely isolated physically from the grid. It's through the AC to DC, DC to AC. So even the rotor revolving not at 60 Hertz, you can easily change the frequency to the same as the grid. This figure does give the idea on how the operating of the induction motor from the motor region to the generator region. So this is the similar speed, is the frequency of the grid. So if you operate lower than that speed, that behaves like motor. If it's higher, there will be a generator. So when you have this resistor, if you increase the resistor, resistance, so this range, which is stable operating region, will be wider. So you can utilize to control the stability. All right, so we'll continue on Friday.